Okay, so today's speaker is Xin Li from the University of Glasgow, and his talk is about what you see there on the screen, groupoids and sister algebras arising from Garside categories. So please, Xin Li, go ahead.
Okay, great. Yeah, first of all, thanks a lot for the invitation. It's a great pleasure to give a talk in the seminar. So what I would like to do today, essentially, the goal is to present or discuss class of examples of groupoids and C algebras, which are constructed from these so-called Garside categories. So these Garside categories, or more general Garside structures, they arise naturally in algebra and geometry. But the surprising observation is that actually they explain or sit behind many of the constructions we know in C-star algebras as well. So that turns out to be the case. And in a way, these structures, they help us to organize and unify several example classes. And also, maybe more interestingly, they also allow us to prove results about these groupoids and C-star algebras. So some known results, but also you get new results using that structure. So this is very roughly the idea I want to explain, and hopefully that will come across in my talk. Okay, so I'll start with a very well-known construction, namely of reduced group C-star algebras. So constructions as follows: take a group, say discrete, and you construct, first of all, the left regular representation. So you let the group act on itself by left multiplication, and then you form the Hilbert space L2 of G, and you use this multiplication to, first you can start off by shifting around the basis vectors. So the deltas are the canonical orthonormal basis. And then you observe that this map given by left multiplication, that it extends, in our case of a group, each of these lambda g's extends to a unitary on this Hilbert space. And this assignment g goes to lambda g is called the left regular representation. And then you just collect all the unitaries you see in the image of this representation, and that will generate a C-star algebra for you of bounded linear operators on L2 of G. And that's what we call the reduced group C-star algebra of G. So that's a very classical object. And basically what you can now do is look at this construction again and ask yourself, what is sort of the minimal requirement you need to perform this construction? So for instance, you observe that having a group is not necessary. So you're not using that the elements have inverses. That's not necessary to do this construction. And what you observe is that this construction actually works whenever you have a small category with some assumption that allows you to say that your representation will be by bounded operators. So for instance, this condition of left cancellation would be sufficient. So let me briefly explain what this means. So small category really means sort of the object that has the minimum requirement of having some sort of multiplication defined on them. Okay? So let me give you the precise definition, or at least sketch the idea. So category says just a set, and then you have two maps, target and domain, from this set to itself, or rather to a subset, which we think of the objects. And you view as an element in C as an arrow pointing from the domain to the target. And then on this set there is a multiplication defined, but it's only defined when the two arrows can be concatenated. Yeah. So if the domain of one is equal to the target of the other, and then you get a picture like this, and yeah, and the product then you think of as concatenation of these arrows. Yeah. So this is very roughly the structure we want, and yeah, left cancellation means precisely this condition, that if you take a fixed element and look at the left multiplication map by this element, then this is yeah, satisfies this injectivity condition, if you like. Yeah. So of course this condition is to be understood only if the products make sense. So if the targets of x and y match up with the domain of A. Yeah. So very roughly speaking, it means that left multiplication is in a sense an injective map. Okay. Yeah, and then once you have the structure, you can go back to the construction of reduced group C star algebras and perform exactly the same construction. So you yeah, again look at little r2 of this category. Category viewed just as a set. We form the Hilbert space little r2, and then you, whenever you're given an element in the category, you first of all shift around the basis vectors by left multiplication whenever that makes sense, whenever domain and target match up. Yeah, if they don't match up, you just define the map to be 0. And then you again check that because of left cancellation, this assignment defined on the basis vectors actually extends to a bounded linear operator. So in our case, these will actually extend to partial isometries. Yeah, so in principle, you could even think about even weaker conditions that allow you to extend to bounded linear operators. But for the purpose of this talk, let's just yeah, look at this condition of left cancellation. Okay, and then you do the same thing as before. So you take all these partial isometries that you see in the image of this representation of C, you collect them, and this would generate a C star algebra of bounded linear operators on this Hilbert space, and you can take that as the reduced C star algebra of your small category. Okay, so this is a very general construction. Let me maybe do one concrete example. So for instance, you could take as your category actually a monoid, so you only have one object, and yeah, what I wrote here is the free monoid and two generators, A and B. Yeah, so I denote this with a plus to distinguish it from the group given by certain generators and relations. So it's a monoid we're looking at. And when you take this monoid and look at the left regular representation in its C star algebra, then, so first thing is, because the monoid is generated by two elements, the C star algebra will be also generated by two partial isometries, or in this case, actual isometries. And what is the sort of defining or characteristic feature of these two isometries? The thing is that they have orthogonal ranges. Yeah. So this you can understand in terms of the monoid, because if you left multiply by A, then you get a word starting with A, and if you left multiply with B, you get a word starting with B, and there's no word starting with both A and B, because you're in a free situation. So that's why you get orthogonal ranges. And it turns out that this relation is actually the defining relation. So there's no more relation. In other words, you're just looking at the C star algebra generated by two isometries with orthogonal ranges. And so this is a well-known C-star algebra. It's the triplets version of the Kunz algebra O2. Yeah, so you have an extension like this. You have a quotient map onto O2, which you divide out as the compact operators. And yeah, so how do you see this exact sequence? Well, it's because, I mean, if you want to go from this C-star algebra to O2, then the additional relation you need is that not only the range projections are orthogonal for A and B, but they also have to sum up to 1. Yeah, because then you get the usual relation defining the Kunz algebra O2.
Let me ask you a
Yeah.
short question. If you have a category, small category, you can associate a ring by adding up, taking the direct sum of all the homes and defining the product.
Yes, like the group ring or the
and
monoid ring.
if you cannot compose, it's 0.
Yes.
If you do this with your left cancellative category, which I understand means that all maps are monos. So if you do that and somehow complete this, do you get your algebra? Or is it different algebra? I mean, the other thing is,
yes. So, I mean, you can look at these lambda A's, and you can take the like linear combinations of these with complex coefficients, say, and then I think you get the object you described with complex coefficients. But you will get, I mean, if you complete it, you won't get the C-star algebra because the adjoints you won't see.
you need to add the adjoints.
Yes. Yes. Yeah, but that's right. So yeah, in principle, I mean, you can form the C-star algebra, but there's also there's various algebraic objects you can assign to these things, and they sort of sit inside the C-star algebra. Yes.
Okay, thank you.
Okay. Yeah, so this is the relation between our C-star algebra and O2. And yeah, so what this tells us is that actually, typically, I mean, the C-star algebra we construct from the category, that's interesting, but sometimes it's even more interesting to look at such quotients like O2. And yeah, I won't go into detail too much, but let me just say that there is a general procedure to form such distinguished quotients. So these are also called boundary quotients related to Axel's theory of tight filters, tight quotients, and so on. Yeah, I won't say too much about this, but that for any category in our sense, you can always form these distinguished quotients, and these turn out to be, well, for certain purposes, more interesting because, for instance, there's a better chance for these to be simple and so on. Okay. So far so good. So we have now a very general construction, but essentially what I would like to do is to step back, because this construction is very general, but if you want, it's too general. So I mean, you're constructing something from any small category with some left cancellation, say. So it's a very general framework. So I mean, you can imagine it will be hard to prove interesting results in this generality. And so this is somehow the point of the talk, that we try to find good classes of examples. Good meaning that, well, they should cover interesting special cases, of course, but then they should be small enough so that you can prove results about them. Yes, so, and essentially in this talk I will present one such class of examples. Okay, So here is a little picture of the kind of examples I'm thinking about. So there are various classes of examples, which I will in a minute go into more detail and explain the C algebras we construct. And then the question will be, what is sort of the thing that they have in common? So this will be the question mark, which in the middle, which I want to explain afterwards. Okay, so these are all examples of small categories in our sense, to which people have attached C algebras and studied them. So let me explain what these examples are. So on the left we have certain monoids, Artin-Tits monoids, which arise in group theory because they are corresponding Artin-Tits groups. So these groups are related to reflection groups, as I tried to indicate with this picture here. But an example is also what's called the braid group, so it's also related to braids. And it's actually this class of groups where the notion of Garside structure originates from. So I'll say more about this in a minute. And then we have a classical notion of graphs and the corresponding graph C algebras, so in particular Kunst-Krieger algebras. So that's a sort of famous class of examples in C algebras. Then there is a way to go from graphs to, if you want higher dimension objects, called higher rank graphs. Sometimes think of them as colored graphs. So I'll say a bit about them, and you can assign C algebras and prove results which, in a sense, try to mimic results we have for graph C algebras. But then also here we have examples which come more from dynamics. So these are so-called self-similar groups, which are certain groups of automorphisms on trees. And Nikolashevich studied these quite a lot and constructed C algebras. So these are related to these fractals because given such a self-similar group, you can form a certain limit, and then you get pictures like this. So I've just put them there too because they look nice, but I won't talk too much about these fractals. Okay, so that was a quick overview. Now let me go a bit into detail what these things are. So let's start with Artin-Tits monoids. So algebraically, these are monoids which are given by a particular presentation. So you have a generating set sigma, and then you ask for certain relations of this form that you take two generators and you form alternating products. You start with A, and then do the same thing but start with B. And the length of these products, you want them to be the same. So M should be the same. And this gives you the relations you impose. So for the length, you have a choice. So this could any integer starting from 2. But it could also be infinity. And infinity would just mean that you impose no relation between A and B. So just quick examples. So for instance, if you just have 2 generators and your M, the length is 2, and then the relation you impose is just this commutation relation. So you're just looking at the direct product of 2 copies of the natural numbers. If your length is 3, then you look at this relation here, and this is one of these typical braid relations. So in this example, you get one of the braid monoids in this case, and so that's the link to this picture of the braid M I draw. Yeah, or you could take m equals infinity, and that, as I said, means you have no relation between A and B. So then you're back to the free situation of just two generators, no relation. Okay. So yeah, let me try to explain or just give the idea why this is related to this other picture with the reflections. So basically, what's the geometric interpretation of these relations? So here's a way to think about these. So you can think about these generators as reflections across some hyperplanes. So say in Rn. So A is a reflection across certain hyperplane HA, and similarly for B. And then if these hyperplanes intersect at a certain angle, namely pi over m, then you can check that indeed you then get a relation of the form you're looking at. That the product of the alternating product starting with A, m letters, is the same as the one starting with B. So this in a way explains these relations. But so I mean, to go from the presentation I showed you to actual reflections, you need more relations, because the reflections, they will be, when you square them, you get identity. And this is something you don't ask for in the identities relations. So in other words, these reflection groups, they will be quotients of the identities ones. And yeah, so this is the relation to these reflections. Okay, so that was the first class of examples. Yeah, and yeah, I should say, I mean, you can then construct C-star algebras out of these monoids by looking at the left regular representation. They're C-star algebras. So this has been studied quite a lot. For instance, Crispin Larker looked at the case where you have the right-angled case, so m is either 2 or infinity, and proved results about the C-star algebras, and so on. Okay, next case is the graph case. So I will not say much about this, because this is sort of a classical construction. I guess many people of you will know about this. So yeah, so if you're given a graph, then there is sort of a natural way to construct a small category. It's so natural that sometimes, or usually, I just identify the graph with the category, although they're not the same. But the category is just given by the finite paths in your graph. And you multiply them just by putting them together, so you get a longer path, concatenation. And it's in a way a free situation, because you just get longer and longer words, but you have no relations. And so if you take a graph, go to its small category of finite paths, and then perform the construction I told you about. Yeah, if you just take the left regular C-star algebra, you get again the triplets version of graph algebras. And then if you form this distinguished quotient, the boundary quotient, you will get the usual notion of graph C-star algebras. Okay. So yeah, let's move on to higher rank graphs. And yeah, let me first give the definition and then explain the idea. So the definition is this. So now I already go straight away to the small category of paths. So this is actually what I define, not the higher rank graph itself, but the category of paths. And so I say it's a small category, and the important feature is that it comes with a functor from this category to enter the K, to the monoid, free abelian monoid on K generators. And this is sometimes called the degree map. And the important property is this factorization property. So if you have an element in your category and the degree can be written as a sum of two elements in n to the k, then this splitting of the degree, you can explain that in terms of the category. So you can write your element as a product of two things in the category, which each of them give you the individual summings of the degree.
That tiny question: does n have a 0 for you to the natural numbers?
Oh yes, it's a monoid. Yes. Yeah. So you have this, and important thing is that these B and C are unique, and this will actually impose quite strong conditions. So, for instance, it will imply that the category is cancellative. So you have left and right cancellation, for instance. Right. So this is the precise definition, but let me maybe give an idea how to think about these. So first thing is that ordinary graphs are one graphs where k is equal to 1. Yeah. So if you take an ordinary graph, go over to its category of finite paths, then there is a canonical degree map, which is just the length function for paths. Yeah. And then it's clear if you have a path of length m plus n, then you can write it as a concatenation of a path of length m plus a path of length n. You just split it up. And then once you have this, there is sort of an easy way to construct k graphs for any k, because you can just take graphs, ordinary graphs, take their finite paths categories, and just form the direct product. Yeah, this would be a k graph. And here you see sort of the idea behind this business. Yeah, so this, I mean, you could say this is like another graph, but now you have some relations here, because you know that whenever you have something in one of the factors, this will commute with something in the other factor. So this is no longer a free situation. You introduce some relations, but there is quite a few restrictions in order to get a k-graph. Okay, and so this is a special class of k-graphs, and more generally, what's the idea? Yeah, the idea is that you can think of this k-graph as being a graph where you color the edges. You have k colors, you assign a color to each edge, and then you introduce relations between generators of different colors. So this reflects that, the colors correspond to the generators in n to the k. You have k of them, so you have k colors. And the point is that if you add generators, you can add the first one to the second, or you can do it the other way around. But n to the k is a million, so this gives you the same. And because of that, you need generators. If you, for instance, let's look at this picture. So here we have red, yellow, and blue. So if you do red and then yellow, for instance, this has to be the same as going first yellow, then red. So you need to impose these kind of relations to get a k-graph. So that's roughly speaking the idea. And so it's actually quite tricky because you can't just impose any relation. You, for instance, to get associativity and so on, there are some constraints. Okay, so this is very roughly speaking the notion of higher rank graphs. And as before, you can take these objects, construct C-star algebras, and the C-star algebras people have constructed coincide with these boundary quotient of the left regular C-star algebras I showed you. So that's another class of examples. And the last one is, let me explain these self-similar groups. So as I said, a self-similar group is a certain group of automorphisms of a tree, more precisely of a rooted tree. So you look at tree automorphisms preserving the root. And because you ask for root preserving automorphisms, the group has to permute the subtrees at each given level. So this is sort of the rigid situation that you have. So maybe with a picture. So for instance, if you have a subtree at this level 1, then it has to be sent to another subtree of level 1. So in this case, there are only 2 choices. So say, for instance, this one is going to this other blue one. Okay, so you get a automorphism of these subtrees. But each of the subtree is again canonically isomorphic to the big tree. So in other words, the restriction of your group element is another automorphism of the tree. And this is precisely the notion of self-similarity, that you ask these restricted automorphisms to again lie in the group itself. And then your group is called self-similar. So as I said, and I won't go into too much detail, but these arise in dynamics. And Nikolashevich constructed C-star algebras for them. So let me explain how to connect his construction of C-star algebras to this construction I explained of left regular C-star algebras for small categories. So what's the category? What's the small category attached to this? So what you do is this. So the group acts on a tree, and the tree you can identify with the free monoid on D generators, where D is the degree inside your tree. And because the group acts on the tree, this will induce for you an action of the group on this monoid under this identification. And so this will be an action, but not by monoid automorphisms, by something not quite as nice, but it still carries a lot of structure. And this structure allows you to form what's called the Zappa-Shep product. So you have this monoid, and you form the product, the Zappa-Shep product, by this group. Again, maybe I won't go into details too much, but how to think about this. This is another monoid, and the elements can be written uniquely as a product of something in the monoid, in the free monoid, times something in the group. And then to be able to talk about a monoid, I then have to explain how to multiply 2 such expressions. So really what I need to do, I need to move this 1G on the other side of Q, so move it to the other side of a free monoid element. And there's a rule how to move this across, and this is precisely encoded by the self-similar action. So this is the idea how to form this Zappa-Shep product out of this self-similar group.
So is there some cocycle as in the Excel Pardo
situation? Yes, exactly. So Excel Pardo, exactly. They looked at such things, and there's a cocycle which encodes this self-similar action and so on. So I'm not going to too much detail, but exactly that's going on in the background. And and the point is, once you have this cancellative monoid, you can look at its C-star algebra and the boundary quotient, and you observe that this is exactly the C-star algebra Nikolashevich constructed. So in this sense also, this fits into our framework. Okay, so let me just look at the picture again. So now I went quickly through all these examples. And so question, what is sort of the link between all of these? And well, the answer is already in the title of the talk. So it turns out that all these are Garside categories. And that's the next point I would like to make. Okay. So yeah, so I guess what I would like to do is to first explain to you what a Garside category is, and then explain why all these examples I showed you are actually examples of these Garside categories. Okay, so again, I'll first go through the definition and then explain the idea behind this. So for the definition, we need a bit of preparation. So first of all, we start off with the left cancellative small category, say. And then we look at this divisibility relation. Yeah? So we say A is a left divisor of B if the obvious thing holds, if B can be written as something A times another element in the category. And then you can also talk about strict divisors, where A divides B, but not the other way around. And one way to say it is that A divides B, but A cannot be written as B times an invertible element. So this is another way to say it. This is strict divisibility. And then there is a finiteness property you can ask whenever you have this relation. So say left Noetherian means that you cannot find an infinite chain in your category of smaller and smaller divisors. So this is one condition that we will need in the definition of Garside categories. And then the other ingredient is this notion of MCMs, minimal common multiples. So you have two elements in your category, and you look at common multiples. Yeah, this is the reverse of being a divisor. So A and B should be divisors if you are multiple. And then you look at elements which are minimal among all these common multiples. You call this minimal common multiples, MCMs. Okay, so these are the two ingredients. And now here's the definition. So you start off with this left cancellative category, and you assume it's Noetherian. So what I explained to you was left Noetherian, but you can define everything with right divisors and get a notion of right Noetherian, and you want both for C. Okay, so both sides. And then a collection of elements S in C is called a Garside family if you have the following. So S should generate your category whenever you add in the invertible elements. Okay, so this is one requirement. And then if you take S and again enrich with invertible elements from the left and add all of these, then this should be a set which is closed under these minimal common multiples. Yeah? So if you have two elements in this, essentially in S, then the minimal common multiples should also be contained in there. And it should also be closed under right divisors. So right divisors being essentially the same as left divisors, but from the other side. Okay, so this is a definition, but maybe it's not so important. Let me try to give the idea behind this. So the point really is about this, that given such a Garside family in C, there will be what's called a normal form for elements in C. And this is really the crucial thing. So assume you have a small category and a Garside family, then what this gives you is that every element in C can be written in a particular way as a product of essentially factors in S in this Garside family, up to invertible elements. And what's special about this product is that you have this greedy property that whenever you take a sub product of these S, starting from J, and whenever you take an element in S which divides this subword, then this element in S has to divide the first factor. So really what you do is you take an element C, and you take the biggest divisor in S out of C. This is S1. And then you do the same thing for the rest. You take out as much, the biggest divisor in S you can find in the remainder. And you take it out after finite many steps, it will stop, and it will give you a normal form product description for C. And there's a certain way to say that two such normal forms are unique if they describe the same element, and so on. So this has various names called greedy normal form, or Garside thirst normal form, and so on.
A stupid question.
Yeah.
Doesn't if suppose there are three S's there, doesn't the product of the first two divide the whole thing? Say
you mean a free monoid, or
no? Say you have S1 times S2 times S3.
Yes.
Doesn't S1 S2 divide S1 S2 S3?
Yes, but S doesn't have to be closed under products, if that's what you mean.
R was in S. Okay.
Yes, that's the point.
I was missing that. Yeah. Okay. Thank you.
Yeah, good point. Yes. So S, in a sense, are sort of the building blocks, atoms, if you like, and you build everything out of S. Okay. So, the way I gave this definition so far, it's in a sense empty, because you can always find such a Garside family S. You could take S to be equal to the whole category. Then you get a very sort of stupid normal form, namely C equals C. So it doesn't tell you anything. So in other words, this notion only becomes interesting if S is in a sense small. So you want to find small S. And there are various ways to say when S is small. So for instance, you can ask for this finiteness condition. So this is saying that whenever you have an object and you look at the elements in S pointing to that object with target equal to V, then this should be a finite set. So for monoids, this would really mean you want to find a finite Garside family inside a monoid. Okay, so let me, so this has been studied in algebra. There's a whole book about these things, lots of examples in there. So if you're interested, have a look. So I guess what I should do now is explain to you why the examples I mentioned all have this property, that they are Garside categories. So Garside categories means that they have categories with a Garside family. Okay, so let me just go through some examples for you. So for instance, take the free abelian monoid. Yeah?
There is a raised hand by Ben Steinberg.
Yeah, I can't really see.
Yeah, okay. So, Ben, do you want to speak? Or was it an accident? Okay, so sorry.
Okay, we just continue. Okay.
Can you hear me?
Oh, yeah?
Oh, sorry, my microphone was bad. I was just asking whether you require only finitely many minimal common extensions, or you're allowing to have infinitely many minimal common extensions? When you're looking at these, like you're asking if to be a Garside structure, you have these minimal common extensions, but you care whether they're infinitely many or finitely many, because that often makes a big difference in things. Like this finitely aligned kind of business.
Yes. I mean, I guess I'm not asking in the definition for such a restriction, but then, for instance, if you want to find a locally finite Garside family, then you probably need something like this.
That would force it, I think. Okay,
Yes,
but in general, you're
yeah.
not requiring it. Okay.
Yeah. But as I said, this notion will only be interesting if you kind of find a small Garside family.
I mean, I vaguely remember when the group theorists talk about this. I think S is always finite, so these don't come up, these kinds of issues.
Yeah, I'm just following this sort of general. So I mean, they in this book they sort of develop it in very general terms. But yeah, you're right. So in general, I mean, usually you want S to be small in a sense. Yeah. Okay. So some examples. For instance, free abelian monoid. So there you can take for S this finite set A, B, and AB. AB and the product AB, and the idea is that essentially whenever you have a word, so here I'm trying to give an example of a normal form, you just take out as many powers of A times B as you can, and then if you can't do any more, then you're just left with either A or B, and then you just add that, and that's the normal form. Yeah. So this is one example. If you have a free situation, then you can get away with even a smaller set, maybe just the generators. And then the normal form will just be the usual way you write elements in the free monoid as words in A and B. Okay. For graphs, what you can do is just take for S the edges, yeah, and then use that any finite path in your graph is a unique product of edges. Yeah? This is how we think about this finite path, and this will be the normal form in this case. So how do we understand K-graphs? So this is now an observation that this notion of Garside family plays very nicely with these degree maps. So this is a general observation that if you have a category and you have a degree map, and the target, if that's a monoid, like in our case n to the k, and you know that you have a Garside family in this monoid P in the target of the degree map, then you can just pull it back, take the pre-images, and this will be a Garside family in the original category.
Are you assuming that this is surjective?
You could, I guess, without loss, assume that. Otherwise, you could take the image, I guess. But yeah.
Because it could be empty. That's the inverse image of your Garside family.
Oh yes. So maybe. I mean, SP will generate P. So unless. Yes. Okay. So maybe it's safer to assume it's surjective.
Well, it can't be empty because of the fact. I guess if you have a factorization property kind of thing, yes, or something, then it won't be empty. But maybe you need a little bit on that degree map to make sure.
Yeah, because exactly, because I mean you can use a factorization map to see that you because SP generates P, and then every element can be written as a product of SP, so they have to be hit. But yeah. So anyways, so this is a general observation, and this explains why, I mean, you can in n to the k you can take similarly as in our example here a finite Garside family, and then you can just pull it back to get one for any k graph. Right. So this is one general observation explaining k graphs. There's another general observation explaining the self-similar groups, which is if you have a semi-similar group, then one part of that Zabachev product we formed was this free monoid. And for the free monoid, as I explained, there's a canonical Garside family. Just take the generators. And then it turns out that in this case, the same set viewed now in this bigger monoid is again a Garside family for the bigger thing. And the reason for that is, we constructed this product by essentially just adding invertible elements. Yeah. So the non-invertible elements, these are controlled by this free monoid, and then the group G will just add more units to this. But adding invertible elements, if you look at the definition of Garside family, doesn't really destroy much, because you're just looking at divisibility and so on. This is not affected by invertible elements. This is roughly speaking the idea why this works. Yeah. Of course, you're using that. The way you add invertible elements is in a controlled way because of this Zabachev product. And because of that, you can make this general observation. So this explains why self-similar groups, the Zabachev products attached to them, are also Garside categories, in this case, Garside monoids. Okay, very good. So this explains why the examples I showed are all fall into this framework. And then I guess, my time is basically up, so I will just briefly say what sort of results you can prove using these Garside structures. So, first thing is, this is a general thing that these C-star algebras we construct, they have groupoid models, so they can be written as groupoid C-star algebras. And the idea is, what's a groupoid? Essentially what you do is you take the category and it has a space of infinite paths. So you look at infinite paths and it has a topology, and the category then acts by local homomorphisms, because you can always multiply on the left some infinite paths by some element in the category, and that will give you another infinite path. So you have this some sort of partial action, if you like, and you can form the groupoid of germs, and that will give you the groupoid model for these C-star algebras. And then the usual game, you can analyze the C-star algebra by analyzing the groupoid. And so for instance, using these Garside categories, you can, for example, classify the closed invariant subspaces of the groupoid. So this will give you a way to say something about ideal structures. You can study amenability, which will be related to nuclearity. There's also other structural properties like pure infiniteness you can study in this context. And for all of these, what's the main idea? The main idea is, because you have a Garside structure, you have normal forms in C. And then you have to work a bit, but this will induce for you a way to talk about normal forms even for infinite paths. Yeah, and so if you have a canonical way to represent elements in the unit space of your groupoid, then you're sort of in business. Then you can understand the space and the action, and then prove results about the groupoid. So this very roughly is the idea, and everything boils down to these normal forms. Maybe just to add, so there's also, together with a student of mine, Alistair Miller, we developed a way to compute K-theory for these C-star algebras. And maybe last thing I'll say is the reason why I started to look at them was actually I was interested in what's called these topological full groups. So these are certain groups, very interesting groups, which you can attach to these groupoids. And in the classical case of the groupoid for O2, the one we sort of touched, the group you get is Thomson's group V. So you get interesting groups in this way. And the reason why I was looking at this is because the Garside structures you can use to prove that certain classes of these groups satisfy finiteness properties. And so they're type Fn or type F infinity. So it's a property that is relevant in homological algebra, algebraic topology. And so Matui proved that for in the Kunst-Krieger case for graphs, you get type F infinity groups, and then I was able to extend that for certain other groupoids coming from Garside categories. Okay, so I think I'll stop here. Thank you very much for your attention.
Thank you very much, Xin, for your wonderful talk. Are there any questions, any further questions from the audience? Let me see if somebody raises his hand. Well, there's some applause there. Yeah. So,
I guess.
yeah.
Oh.
Sure.
Go ahead. Sorry, I didn't mean to interrupt. You started asking first.
No, you go ahead.
I was going to just ask for these finiteness properties. Do you construct sort of an interesting Eilenberg-MacLane space for them, or do you? Because like Brown has a nice construction for V, and for Artin groups, there's of course very interesting conjectures about what their classifying spaces look like. So I'm just wondering, to get these finiteness properties, do you construct a nice space, or is it via a different method?
Yes. So you construct certain complexes where the group acts, and then you prove that there's certain high enough connectivity in these complexes. And
is it similar to Brown's complex, where he's basically building sort of a natural category version of a groupoid? He builds a groupoid essentially that V is acting on, and then kind of filters it to study it. Is it somehow a similar kind of construction, but using the Garside category and building a groupoid out of it?
Yes, it's sort of similar. I mean, it's sort of ideas going back to what happened for V in the classical case. Yes, I think that's right. Yeah.
Okay, it was very interesting. Very, very nice talk. Really, really nice.
Thanks.
I wanted to ask, when you said about the computation, or K-theory computation, I mean, in the case of, say, graph algebras, you have a very simple presentation of the graph sister algebra in KK. You know, there's a triangle involving just copies of C and a matrix.
Yes.
Now, I mean, group sister algebras are famously far more complicated than that.
Yes.
But is there a subclass of this class of algebras that has also a nice presentation, including, of course, graph sister algebras within this Garside class?
Yeah, so that's roughly the idea, that we, in a sense, want to extend the sort of very nice situation for graph algebras. And as you say, the computation will rely on, for instance, that you understand certain invertible elements. Say, for the self-similar groups, for instance, you would have as an input the K-theory for the group sister algebras for these self-similar groups. But if you don't have invertible elements, then typically the formula becomes simpler. But for instance, already for K-graphs, I mean, sort of for graphs, you just get just one 6-7 sequence to compute K-theory, essentially, right? Mm-hmm. But for K-graphs, it already becomes more complicated with increasing K. So in general, you can only expect to get a spectral sequence giving you the K-theory. And then as K grows, it will become more and more difficult to analyze that.
But you still, I mean, can you still get in KK, can you still get from your to your algebra infinitely many steps by taking copies, finitely many copies of the complex numbers and a finite number of algebra extensions? I mean, that you take triangles.
Yes, I mean, so the complex numbers appear if you have no invertible elements, because this will be the group C star of the trivia group in a sense. So if you're in the situation of no invertible elements and some finiteness properties from the Garside structures, then I think there's a way to get it in finitely many steps. The K theory of the C star algebra.
I mean, you also have it for the sister algebra of the integers thought of as a group.
Yes. So then you would, yeah, I guess then
I mean, if the groups are nice, maybe you can also do.
Yes. So I guess in general, what happens is you have the invertible elements, and you can get the C star algebra in finite many steps from the group C star of these invertible elements somehow. This is maybe what happens in the end.
Okay, so are there any more questions that you want to ask that should be in the recording? So if not, we thank Xin Li again, and let me stop the recording.